Okay, so in this from now onwards we will discuss the BJT amplifier. Try to discuss the BJT amplifier in detail. What is the definition of the amplifier, how the amplifier is to be modeled, and what is the equivalent circuit of the amplifier, what are the different characteristics of the amplifier, and the small signal equivalent model of the amplifier in the case of the BJT, and lot more. Okay, so now the topic of discussion today is BJT amplifier. So this is the lecture number 1 of the BJT amplifier. Okay. Now whenever we talk about the amplifier, if we just draw a simple like this, so this is the black box view of an amplifier. So the gain of the amplifier is nothing but your output divided by input. Okay, and this is the output section. Current is I out and voltage is V out. Here the input section of the amplifier. Here the current is I in and the voltage is V in. Now suppose this is your input that is being applied to the amplifier, and the output that we are getting out of the amplifier is like this. Obviously the amplitude is increases. Now this is the simple model of an black box view. We can see that the black box view of an amplifier. So your most important parameter in case of the amplifier is your gain. So gain is nothing but gain is represented by the symbol A, and it is nothing but the ratio of the output divided by input. Now as it is a amplifier can be modeled as a two-port network, so this is your input section and this is your output section. So in the output section there is a current flowing through the output terminal, and the voltage across is V out, and there is a input voltage V in and the current is I in. Okay, now the definition of the amplifier. So it is a circuit that increases the amplitude of AC signal. That increases the amplitude of AC signal. Okay. Now this is the definition of the amplifier. Now amplifier, it is a because it increases the amplitude of the AC signal, because in the case of the amplifier we provide the DC signal as well as the AC signal to the amplifier. DC signal is used for one purpose and AC signal is used for the amplification purpose. Okay, so that we will discuss. So next the amplifier is how the amplifier is increases the amplitude of AC signal. Suppose there is a signal xt, okay, that has been represented as sine omega t. Okay, now if you are familiar with the signal and system concept subject, then the power of this AC signal, power of the AC signal can be represented as like this: x that is, if you calculate the power, it is nothing but a square divided by 2. Okay, so there is another signal, suppose yt, okay, which is represented by b sine omega t plus phi. Okay, omega t plus phi, and if you just calculate the power of this signal, that means the pyt, then you will get the power is nothing but V square divided by 2. So the phase is nothing to do with the power. So this is, suppose this is a one signal, and if you can verify the result with the help of the signal system concept. Okay, so the power of this signal is S square divided by 2, any sinusoidal signal. And in the communication system you will also heard that any kind of modulation, whenever you use the carrier signal, the carrier power is represented by S square divided by 2, like this, amplitude square divided by 2, and this signal is B square divided by 2. Okay, now if here this is the two part, A square divided by 2, B square divided by 2. Now if B is greater than A, suppose this B is greater than A, okay, B is nothing but this amplitude of this signal. So if B is greater than A, then you can say that the PR, okay, greater than, or you can say PY, okay, not PR, PY is greater than PX. So what we are trying to say here is that amplifier increases the power of AC signal also. Amplifier increases the power of AC signal also. Okay, amplifier also increases the power of AC signal. So that is being clear from here. We have assume here B greater than A, because in the case of the amplifier I have said that the amplifier is a circuit that increases the amplitude of the AC signal. Now this is the amplitude of the input signal and this is the amplitude of the output signal. Now as this is the amplifier circuit, input is being applied here, output is being taken out from here. Now as this is the amplifier, B must be greater than A, so that is the condition. And for that purpose, as B is greater than A, so B square by 2 also greater than A square by 2, that's why the power of the output is greater than the power of the input. So we can conclude that the amplifier also increases the power of the AC signal. Now how, if it is a system, if you think of the amplifier is a system, then within a system the power cannot be generated or the dissipated like this. Okay, so how this power will came from? Power must be fixed. Okay, now how this power will came from in the circuit? Now the answer is that amplifier consume the power from the DC biasing. I have said that in the case of the amplifier circuit we have also used the DC signal as well as the AC signal. DC signal is used for the biasing purpose of the transistor in any kind of diode and the transistor for any kind of device. DC signal is used for the biasing purpose and the AC signal is provided for the amplification purpose. Now we have only discussing the AC signal. The AC signal amplitude is increases, so the power of the AC signal is also increases. Now how the power of the AC signal will increases? If the power is fixed within a system. Okay, so this power is came from the DC biasing. So amplifier consumes power. Amplifier consume power from DC biasing. From DC biasing. Amplifier consumes power from the DC biasing and supplies some fraction of power to input AC signal. Okay, and supplies, not all the power being supplied to the AC, supplies fraction of power, to input AC. So that's why power is increases in the case of the amplifier circuit. Okay, so hope you understand it in case of the power, in case of the amplitude, and what is the definition of the amplifier. Okay, so next we will discuss the amplifier model. So amplifier model. So whenever you want to discuss the amplifier model, so suppose this is a simple amplifier model. There is a resistance is there. Okay, this resistance is represented by R in, and there is a gain is there. Obviously this is an amplifier, so there must be a gain, and there is a output resistance is there. Okay, so this is the amplifier. So this is the gain. Gain is represented by A, and this is the output resistance. So this is R out. Okay, this is the signal output, and this is the signal input. So this is the model of the amplifier. Okay, this is a simple amplifier model, can be represented by in the case of the BJT. Now how this can be happen in case of the BJT? So in the case of the BJT, so suppose this is your input resistance and this is your gain. Okay, so as it is an amplifier, so gain is represented by A into V in, so dependent voltage source, and this is the output resistance. This is R out, this is your R in. So this is the model of the amplifier. Okay, now if you want to connect the input and the output, so this is the model of the amplifier. Now if you want to connect the input and output to this amplifier, then load may be connected like this. So this is maybe your load. Okay, not like this. So this is your RL. Load may be connected in the amplifier. So this is your load resistance. Okay, and a voltage source must be connected, like this is your voltage source to the input, and there is a series resistance to the voltage source. This is represented by RS with the voltage source VS. So this is the input source, this is the source, and this is the load. Okay, so how the amplifier is being connected? So this is the amplifier model, and how the source is being connected with the amplifier input, and how load is being connected with the amplifier output. Now in the case of the ideal amplifier, all of you know that here the gain is represented by A, and R out, output resistance, there must be some specification of the output resistance, that must be 0, and the input resistance must be infinite. So why we are saying, we have also discussed previously, and gain is represented by the voltage gain is represented by V0 divided by V in, and current gain is represented by I0 divided by I in. Now these characteristics, output resistance why it is 0, input resistance why it is infinite in the case of the amplifier. So suppose this is a simple understanding. So this is your Vs. So input voltage, internal input voltage, that has been here, this voltage is being represented as V in. Okay, now V in is represented as Vs into R in divided by R in plus RS. Okay, now here you can say that, let's make some space. So Vs into R in divided by 1 plus Rs divided by R in. Now if R in tends to infinite, then your input, whatever input is going to fall at the input section of the amplifier, okay, that is equal to Vs, and that is the criteria we want. We don't want any voltage to be wasted or to be dropped across the Rs. So that's why you must provide the input resistance must be infinite, so that almost all of the voltage that we are providing here must be fall at the input section. So that is the case when the input resistance is infinite, and same logic you can apply, so that you can prove that why the output resistance is ideally be 0 in the case of the amplifier. Okay, so that is the case we want to model an amplifier. Later we will study the different amplifier model in the case of the BJT. Okay, so next the different characteristics of the BJT amplifier, that means the input resistance, output resistance, how the equation will look like, so that we will study now. Okay, so for that purpose we will must import a diagram. Okay, so suppose this is the diagram. Okay, so this is a simple diagram in the case of the common emitter. This is the common emitter amplifier, and in the case of the common emitter amplifier, you can see there is different capacitor is being connected. We have also said the importance of this capacitor. So this is capacitor 1, capacitor 2, capacitor 3, like this. We have also said the importance. This is the resistance RE. So we have said in a lecture previously that why we connected RE and why we connected C3. Okay, I hope all of you remember that the logic here. C1 and C2 are called the coupling capacitor. Okay, so AC supply, in the case of the AC supply, all of you know that the capacitor is being short circuited, and in the case of the DC supply, capacitor is being open circuited. Now we can see very easily, if we want to connect this Vs, this is the input voltage that are providing to the amplifier, that we are providing to the amplifier to be amplified. So if you want this voltage to be connected to the rest of this circuit, then this is the capacitor. So this capacitor, if we provide AC signal here, this capacitor will short circuit this path and it will be connected to the system. Likewise, if you want to get the output signal out of this amplifier, then this capacitor will short circuit the path and we will get the AC output signal out of the amplifier. So that's why this capacitor is called the coupling capacitor. It actually couples the AC signals to the system input, and it will block the DC. It blocks the DC. Any kind of DC is being represented here within the AC, that is being blocked to reach the system, because we only want the AC signal to be amplified, we want the any kind of DC signal to be amplified. Okay, so these are called the coupling capacitor. And there is another capacitor, this is the capacitor C3, and I have also discussed in detail previously why we connected this C3 is called the bypass capacitor, and why we connected this RE and why we connected this C3, because in the case of the AC circuit, we don't want, in the case of the AC analysis of the circuit, we don't want this RE. Okay, we don't want this, 1 minute, we don't want this RE. So that's why in the case of the AC circuit analysis, this is short circuited path and RE would be avoided. But in the case of the RE is used to provide the DC stability, or used to stabilize the circuit. Okay, so it is used to increase the DC stability of the circuit. So that's why we require RE. So that's why in the case of the DC, the capacitor is being open circuited, then the RE is being connected to the circuit in case of the DC analysis. So providing this is your DC. So this case of the biasing, whenever you want to provide the bias point, or want to fix the bias point into the circuit, then this RE comes into picture and fix the bias point within the circuit. And then whenever we want to perform the AC analysis of the circuit, then this AC analysis, this capacitor resistance is being bypassed with the help of this capacitor. So this C3 is called the bypass capacitor. This C3 is called the bypass capacitor. Okay, so this is the all about the how this is called the capacitor, and how this RE is called, why C3 is called the bypass capacitor, and how the being importance. And okay, I'm just removing all this. Okay, so next, suppose whenever we perform the AC analysis, I have said that we have to short circuit this DC. So we have to short circuit this DC in the case of the AC analysis. So suppose this is being short circuited to ground, This is the only the DC signal provided in the circuit. So if this is the simplification of the circuit. So this RE is being connected. In the case of the AC analysis, this RE is not present because there is a short circuit path, so you can remove this RE also. Okay, so this RE is being removed, and there is a RC that is being connected to ground, and this is also a resistance is there that is being connected to ground. This is R2, and this is the RS, and this is your VS. Okay, so this is your R1, this is your R2, this is your RC, this is your RS, and this is your VS. So this is the, whenever you perform the AC analysis of the circuit will look like this. So if you further simplify the circuit in a different way, then it will look like something this R1 and R2 are connected to ground, so these two are parallel, and the RC is also connected to the ground. Okay, so the circuit will eventually look like this. So this is your circuit. This is your RS, this is your VS connected to ground, and I have said that the R1 and R2 both are in parallel. So R1 and R2 both are in parallel because R1 is also connected to ground, R2 is also connected to ground, so both two are in parallel. And this is your base emitter collector. Through the collector there is a resistance that is also connected to ground. So this is your RC, this is your V0, and this also connected to ground. So this is the circuit look like something in the case of the AC analysis. Okay, we have short circuit this thing, and different characteristics associated with this, the input impedance, output impedance. Now the different characteristics to be studied in the case of the AC analysis. Through the AC analysis we will try to study the different characteristics of the amplifier. First we study the input impedance. Now in the case of the calculation of the input impedance, we must remember the input impedance in the first parameter, it is represented by your Zin. Okay, now Zin is represented by Vin divided by Rin. Vin divided by In. Now there is a condition is there, it does not include the RS. How we will calculate Vin and In? Now just look into this circuit. This is your suppose this is your section, and this is the I want to calculate the Zin like this, and this is the Vin, this being dropped Vin. Okay, and this is the current being flowed into the circuit, I. Okay. So whenever you want to calculate the Vin and In, you can see whenever you want to calculate the Vin and In, then we don't include this RS resistance. So that is the condition it is the condition that whenever we calculate the input impedance, RS is not be included into the circuit. So that is also the same case of the output impedance. That is the another parameter to be studied in the case of the AC analysis. So in the calculation of the output impedance, so output impedance is Z out is V out divided by I out. So in this case also there is a condition calculation. So what is this condition? This condition is that we don't want to include the load resistance. If there is a load resistance, we don't want to include that because this is V0. So if there is a load resistance is present in this circuit, suppose this is RL and the current is flowing through this I out. Okay, so this is your V0. So in the case of the calculation of the output resistance, that is the Z out. Okay, we does not want to include the RL. So calculation we will later study how it will be calculated. So this is the first point, that calculation of the output impedance, the load resistance must not be included. So that is the condition. Next, the voltage gain. There is two type of voltage gain is there. So voltage gain AV is V out divided by V in. Okay, now V out divided by V in is the actual voltage gain. Now if you want to calculate the overall voltage gain, so that is AVS. It is represented by VS divided by V out divided by Vs. So the difference is that here this is your V in, so that is different from the Vs, that is somehow different from this Vs because of this some drop here. And if you want to calculate the voltage gain, that is the V out divided by V in. This is the diagram, V out divided by V in. Okay, and if you want to calculate the overall voltage gain is V out divided by Vs. So that is the parameter we will see in due course, that how is being this parameter is being calculated. So before calculation of this parameter, we will first have to model the transistor and replace the model with the help of this transistor, so that simple network analysis can be applied. And if you have a good command over the network analysis, then this calculation of this parameter is very much simple to use. So this is the parameter we will try to study in your AC analysis, okay, or the small signal analysis. And so before discussion of this analysis, we will first discuss what are the different models available for the transistor and try to replace the transistor in the circuit. This is the transistor still available in the circuit, so we will replace the transistor with the help of this model, suppose the Ebert small model or like that T model. So we will try to replace the transistor with the help of this model and then perform the simple network analysis. Okay, network analysis means the KCL, KVL, this type of equation. We will try to perform this type of equation within the circuit and try to find out this parameter. Okay, so from the next lecture onwards, we will try to find out the transistor model and then calculate this parameter. Okay, thank you.